All right, kiddos, let's take a look at the patterns that we noticed in series circuits. Okay. What you probably noticed is that the total current for all of the circuits seem to stay the same, right? The total current was the same as the current running through a 1 light bulb circuit, was the same as the current running through each light bulb in the 2 light bulb circuit and the 3 light bulb circuit. So remember that we use a capital I as the abbreviation for current. The second thing you probably noticed is that in a circuit, the total voltage, right? The total voltage is the power supply voltage. The total voltage in a 1 light bulb circuit is equal to the voltage across that 1 light bulb, right? They were both the same voltage. However, in a 2 light bulb circuit, the power supply total voltage required to keep the light bulb up at the same brightness increased. So you take the voltage across each of the light bulbs, add them together, and you'll get the total voltage that the power supply supplies. And then with 3 light bulbs, you have this. Okay. So now with a little aside, let's go to the side here. Aside, we've got a thing called Ohm's law at play, right? So Ohm's law says that in any circuit or across any light bulb or resistor, Ohm's law follows V equals I R. So voltage equals current times resistance. Okay. There are some resistors that are non-linear, that don't follow this law. And so primarily for our studies, we'll be looking at resistors like light bulbs or other devices that are considered ohmic. Okay. If you plot voltage versus current across a light bulb or another resistor, you should get a proportional relationship where the slope is equal to R, the resistance. Okay. And so we call the relationship when the relationship between V and I is proportional with the slope of R, that's ohmic. Sometimes you will see the slope decreasing as the voltage and current increase. The slope will be decreasing, and this relationship is non-ohmic. And you won't have to do anything with that other than recognize whether a relationship is ohmic or non-ohmic. Okay, so if we know Ohm's law, V equals IR, and I'm going to box that because that's an important relationship that we'll use a ton over the next couple of weeks. If we know V equals IR, right, then we could say, what if we, instead of V in this equation, what if we wrote IR, right? What if we wrote, instead of V total, we wrote current total times resistance total. and that equals current 1 times resistance of light bulb 1 plus the current going through a second light bulb, times the resistance of the second light bulb plus current going through the third light bulb times resistance of the third light bulb. Okay, so we're getting somewhere. Now, what do we know about all of the currents? We know that they're all the same, right? They're all equal. So this I total is the same as I1, the same as I2, the same as I3. So that means they all cancel out. And so we've got now, conveniently, a relationship for total resistance in a series circuit. Okay, so we've got 3 relationships. Relationship between resistance and voltage and current in a series circuit. All right, and I'm boxing those. Now in your lab, I want you to calculate total resistance a couple of ways. Okay, so you're going to find it actually first this way. You should have written down the resistance of each of your light bulbs, right? Add them up. What's the total resistance of your circuit? Okay. The second way, there are a couple ways to do this. You could take, actually you could solve for total resistance by taking that total power supply voltage and dividing it by the total current running through the circuit. Okay, and that's just a rearranging of V equals IR. All right, so that's the calculation that I'd like you to do on your light bulb lab. All right, now how does this make sense? Okay, I'm gonna erase these guys here and actually draw a circuit. So just a moment. All right, I've added to the screen a poorly drawn circuit diagram. But what you see is you've got your power supply and 3 light bulbs in series. Okay, here's our ammeter, and just by convention, the ammeter is always drawn directly next to the positive terminal of the power supply. And I think what you guys found was that the voltage across the power supply, if you had 3 light bulbs, had to be 27 volts or thereabout, because the voltage across each of these light bulbs was 9 volts, right? Okay, and then you've got your current, the total current, IT, going this way, right? Now, where is that current? Current is the charge flow rate. Now, you can also think of current like water, right? Is there any place else for this current to go? Right, so this would be the current flowing through light bulb 1, the current flowing through light bulb 2, the current flowing through light bulb 3. Is there any place for any of those charges to split off and go anywhere else? No, right? All of the electrons that went through this ammeter were the same as all of the electrons that went through the first light bulb, and were the same as what went through the second and the third light bulb. So that's why it makes sense that all of these currents were the same. There is no place else for that charge to go. Okay, now what about voltage? What about voltage? Okay, I want to give you a little bit of information here. Voltage provides what's called a potential drop, right? The voltage across each light bulb or resistor decreases the potential of the electrons in the circuit. Okay, so the voltage across each light bulb decreases the potential of the electrons in the circuit. The total potential drop provided by the resistors must be equal to the voltage across the power supply. Okay, so potential is an electron corollary to energy. So we can think of potential like electrons' potential energy. And what do we know that light bulbs or other resistors provide? They provide resistance. What does resistance do? It's just like friction. It takes away that energy and turns it into heat, right? So if we start out with 27 volts of potential, right, of energy per unit charge, the first light bulb will take out 9 volts of that energy, of that potential. The next light bulb will take out another 9 volts, and the next light bulb will take out another 9 volts. Okay, and so if we think about this, really, 27 volts was the potential difference. The positive side was actually 27 volts. The negative side of the power supply is 0 volts, right? So we start out with a lot of energy per unit charge. It's decreased through the first light bulb, through the second light bulb, through the third light bulb. And then by the time the electrons get through the last light bulb, how much energy or how much potential do they have to have? 0. Okay? And so you can kind of think of this like a waterfall, where it's a waterfall where you start with a lot of potential energy, right? A waterfall where you start with a lot of potential energy, right? Because you've got a lot of height, and then you lose energy, and then you lose energy, and then you lose energy, and right here you've got 0 potential energy. Okay. All right, let's look at parallel circuits. All right, here are 3 light bulbs in parallel circuit, 9-volt battery attached, and our 3 light bulbs set up in parallel with each other. One of the things you probably noticed is that when you measure the potential difference across the power supply, it was 9 volts. And when you measure the potential difference across any any light bulb, that was also 9 volts, right? So we'll say all of the voltages across each of the batteries are equivalent. But you may have noticed for the current, the total current was 2.7 amps, right? That was the total current. But the current that would go through each light bulb was 0.9 amps, right? And so you should have seen that the current total was 2.7, was equal to the current through each of the light bulbs added together. And that makes sense. Just like if you have a river, right, a big river that splits off into smaller rivers, some of the current will go down one path and some will go down another path, but the total water will still add up to how much water was going through the big river.